Okay, so now we're going to get into the math in C. Math in C, most everything is just like MATLAB, plus, minus, multiply, divide. It doesn't do the array math that MATLAB does, but scalar math looks just exactly the same. The percent in C is the modulus, so it'll give the remainder. So if you divide 7 by 2, you get 3 with a remainder of 1. So this is 1. So MATLAB has a different way to do modulo, but this one is useful for seeing if things are even or odd. It's usually where that comes up. There are two things that should be in every program but are mostly in C and C++. These are the increment and decrement operators, plus plus and minus minus, and then plus equals and minus equals, these variations. What this is in many programming languages, a statement like x equals x plus 1, which algebraically doesn't make sense, but it means take the current value of x, add 1 to it, and store it back in x. These are used for counters and indices. Lots of reasons to use this in a computer program. And so since this comes up a lot, there's just a shortcut to it. So x plus plus is exactly the same as typing x equals x plus 1. So you can type this or you can type this, and your program will work exactly the same, but this is shorter. And so you'll see this in a lot of C programs, x plus plus, in loops and places like that. It's the reason that C++, the language, is named C++ because it's one more. It's the next iteration of the language C. So there was no language C+. It went to C++. It went from C to C++. So there's a little programming joke for you today. All right, so plus equals and minus equals and times equals, these are similar, but instead of adding 1, they will add whatever. So x plus equals 2 is the same as x equals x plus 2. If you did x times equal 2, it would be the same as x equals x times 2. So the operator there and the number there, operator there and the number there. So they're just shorthand. Really, really useful shorthand. So logical operators in C are similar in MATLAB. This is for if tests and things like that. So less than, greater than, less than or equal to, greater than or equal to. Not equal to is the exclamation point. This is different than MATLAB. And if you're testing that things are equals, you have to use the equal equal. It's not technically wrong. It won't give you a syntax error if you use the single equal, but it won't do the logical test. It does some other math. So this is a really common mistake, and actually most compilers will warn you about it, even though it's not actually forbidden. It's almost always a mistake. So if you want to see if x equals y, use the equal equal. For logical and logical or, you use double ampersand and double pipe like this, like MATLAB. Not is the exclamation point. In general, the false statement is going to evaluate to 0, and true will be 1, but anything not 0 also evaluates to true. So you can do things like while 1 and if 1, and that's always true. You'll see that sometimes for breaking up code in debugging. So with if tests, you do need curly brackets for your test. You need to put the test itself in parentheses, but this is a complicated logical statement. If x is greater than y and y equals 3, not y equals 3 is what that's saying. So you could do this, or you could do not equals 3. It's the equivalent, and both of those have to be true for this thing to run. So if you've seen the if test in MATLAB, you can also write the if test in C. They're very, very similar. In a C program, you have to put parentheses around the test, and then you have curly brackets for the true, and the else case, if you have it, also has curly brackets. In MATLAB, the parentheses here would be optional, and you'd use if, else, and then the end for the end of the else statement, or the end of the if statement, either one. So just curly brackets instead of end, and make sure you put parentheses on your C program. All right, so let's take a look at loops in C. So a for loop in C looks very different from a for loop in MATLAB, and it's a little more confusing to read, a little bit more flexible when you compare the two. So right here we see a for loop in a C program, and it's got three parts to the for loop. So up here in the parentheses, you have to have three statements separated by semicolons. And the first one is the start condition. So that's normally initializing the index to 0 or whatever we want to start with. The second statement is a logical test, and we keep going. The for loop will keep going as long as this test is true. So normally that's checking to see if the index has reached the limit or not. And then the third statement is what to do after every loop. So normally incrementing the index, count plus plus here adds 1 to count. But you can actually do anything in here, and it will start with this, keep going as long as this is true, and do this at the end of every loop. But this is a regular for loop that counts. It's traditional in C that everything starts with 0. Indices in arrays and things start with 0, which is different from MATLAB, which traditionally starts with 1. So normally they're written as starting from 0, and then they keep going as long as the count is less than 7. So this is going to go 0 through 6, which is going to be 7 times through the loop. So the less than there tells you how many times through the loop, but remember count will not get greater than 6. And then we have curly brackets because it's C, and whatever is done in the curly bracket does every time through the loop. So if we look at this same C code that we saw before, we can convert it to MATLAB. If you're more familiar with MATLAB, we have a for statement, and then we just define the count here going 0 through 6 in MATLAB, and we have the code to execute, and end is the end of the loop. So instead of the word end, we have curly brackets in C, and instead of this list of numbers to count through, we have these three: the beginning, the end, and what to do each time through the loop. There are other kinds of branches and loops, so we've looked at if statements and for loops. Those are by far the most common branches and loops to use. But there is a while loop, where as long as the logic test here in parentheses is true, then this code will execute over and over again. So it's possible to get stuck in an infinite loop, or if you want an infinite loop, you can use a while loop. While 1, if you put a 1 in there, is an infinite loop by definition. So sometimes you'll see that when you want to hang the code. The switch statement is a branch that has several options. So it's used often for things like mode changes. If you have a drone autopilot and you want to go from takeoff mode to cruise mode to landing mode, this is a nice way to divide out your function calls. So we use the word switch, and then in here is something that we're evaluating, either an equation or just a variable, and then whatever this matches on the case statements, we run the code. So if numx is 1, it runs this code. If it's 3, it runs this code. There's a default case. If it doesn't match any of the cases, it runs the default. Switch is kind of strange in C because if it runs case 1, if you don't put the break statement in here, it will fall through and run all the rest of them, which is not normally what you want, but I guess it's a feature if you want to do certain case structures. So the traditional way is to have a case. This has a colon, then the code that runs for that case, and then the word break with a semicolon. And again, all in curly brackets. Arrays are a really common thing to use in a C program, except on something like an Arduino that just doesn't have very much memory. But it's an array, are common in MATLAB too, so hopefully the concept is familiar. The syntax is slightly different. We use the square brackets for the array index rather than parentheses. And when you declare an array, you can declare its size using square brackets with how many elements you want. Then remember that indexing is going to be starting with 0. The first element is going to be PWM out index 0, and the last one is PWM out index 7. If you actually try to access the 8th one, that's the 9th row, element 8, in regular C, it doesn't have a lot of protections against running over memory like that. So you'll find whatever is stored next in the memory on your chip if you have an index out of bounds. So you have to be really careful with arrays because there isn't a lot of checking in order to keep things efficient. You have to build your own checks in. So anyway, this is a for loop that goes through all the elements of an array, setting them all to 0. A two-dimensional array, rows and columns, normally is indexed again a little bit differently. We use two sets of square brackets. So the row and then the column would get indexed that way. And this is how you would initialize the array or declare the array. And this is how you could access it in a nested loop with index I and j in the rows and columns. Again, be really careful if you're using the Arduino Uno or Nano. Have very limited memory, so you can't store 1,000 of anything very easily. Okay, so this last topic is a little bit complicated. It's talking about binary math. So these are bitwise operators. So we don't use them very much in standard C programs at all, but they do come up in microcontrollers because often in a microcontroller there's a memory location where flags are set. So there might be some memory location that's an 8-bit number like this binary number that we're seeing up here, and the bit 0, this first bit, is used to turn something on and off, and the second bit is to configure something else. And so it's an efficient way to store setup and configuration flags by looking at individual bits. If you only need to know yes or no, you only need a single bit. So sometimes a bunch of flags are combined together into a single 8-bit number, and that's the smallest thing that C works with very in a standard way. So sometimes what you need to do is turn on a bit, set it to 1, or turn off a bit, set it to 0, without affecting the other flags that are stored in that location. So this is a common thing if we're trying to set up, for example, the I/O pins on the Arduino. There's a direction register that sets whether the pins are inputs or outputs, and they're groups of 8. That makes a port. So if you want to make a certain pin an output, we have to do this kind of thing. Arduino handles it for us. We have functions that do all of this. So you don't necessarily see this with the Arduino until you start digging into the code itself, the Arduino libraries. But it's a good exercise to see how this works. So we have and OR, and these are bitwise. So they go bit, you need two numbers. So like down here we have a binary number and another binary number. And if you and or OR, you and OR each individual bit and come up with an individual bit. So you do this 8 times and come up with a new 8-bit number. So a single ampersand and a single pipe are bitwise and OR. You have exclusive OR, which means one or the other but not both. And you have NOT, which just flips it from 1 to 0 or 0 to 1. And then we have these shift operators. So this shifts right. It's like moving the decimal point in a decimal number, multiplies by 10 or divides by 10. This does the same thing but to a binary number. So it's actually multiplying by 2 or dividing by 2. One of the first flight controllers I ever designed and wrote software for was written all in assembly language. We didn't have a multiply. We couldn't do that. So we had to set up all the feedback gains as powers of 2, and then I used these shift. So our gains could be 0, 1, 2, 4, 8, and so forth, and then we shifted them. And if we needed something like 6, we could add things together. But we didn't have an easy multiplier, so I had all these codes written that use these things. But fortunately these days we have good compilers and you could do all the math with floating point numbers. But this is a shortcut to move the bits so it shifts the whole number to the left or to the right, just like moving a decimal point in a decimal number. So remember, our goal is to set a bit to 1 or 0 without affecting the others, or set and so it's really a boilerplate is the way I think of this. These two commands, port B is the thing that we're changing, and bit 2 is the bit that we're changing. And this port B or equals 1 left shifted 2 places will set bit 2 to a 1 without affecting the other bits. So this is the short answer if you want to do it. So if you see these, you'll see these all over the place. It's setting bit 2 to a 1 and leaving the other bits alone. This port B and equals not 1 left shifted 2 places sets bit 2 to a 0 without affecting the other bits. It's important to remember that when we number the bits, we start with bit 0, and bit 0 is the rightmost bit. So this is bit 0, bit 1, bit 2 right here. So this is what we're talking about. So if you want to change bit 3, you would change this 2 to a 3. If you want to change bit 4, change the bit to a 4. So you put the bit number here or here, and you use this little template to turn it on or off. If we look at how it works, we see a 1, and we left shift it the right number of places. So here's 1 in binary, an 8-bit binary number. Here is 1 left shifted 2 places. So we've moved the decimal point over 2 places. So from 1, it's now in the 1's place, in the 2's place, in the 4's place. So it's gone from 1 to 4. So that's 1 shifted 2. And that's what we get here. So to turn it on, we OR the original 8-bit number bitwise with 1 shifted 2 places. To turn the bit off, we AND the original number with this 1 shifted, but it was inverted first. So this not 1 left shifted 2, it's complicated to say. You take each bit of this number and invert it. So the zeros become 1s, the 1 becomes 0s. So that's what this right-hand side of these equations mean. And then to OR and AND them, you would break it down to this. So then we do the bitwise OR of the original port with this shifted thing, or we do a bitwise AND of the original port and this shifted thing. That's what AND equal and OR equal. Remember back to plus plus and plus equal and those kinds of things. Just a whole bunch of operations all in a very short amount of time to see what's going on. A bit ORed with 1 always becomes 1, whether the original bit was a 1 or a 0. You need 1 or the other to be 1, and you get a 1. And so if we OR it with a 1, we turn it on. And if you AND something with a 0 bit, it always becomes 0 because both the first bit and the second bit have to be 1 in order for the output to be 1. So if you set this to 0, you'll always get a 0. So let's look one more time at the details here. Again, you'll probably never use this, but it is an interesting exercise, and it explains this complicated thing that you do see if you dig into code. So if we want to set bit 2 high without affecting the other bits, here's our original port B. There's bit 0, bit 1, and bit 2. So bit 2 is a 0, and we want to turn it on, and we want to leave the rest of the bits alone. So this command does it. That's all we really have to know. But again, we take 1, we shift it 2 places, we pad it with zeros, and then we OR it together. So here we take the original port B variable and we OR it bitwise with this 1 shifted 2 places, and we go bit by bit. So 0 ORed with 0, 1 or the other has to be a 1 to get a 1, and they're both 0, so we get a 0. 1 ORed with 0 gives a 1. 0 ORed with 1, 0 or 1 have to be a 1, and it is, so we get a 1. There's our change. 1 ORed with 0 gets a 1, 1 ORed with 0 gets a 1, so you see this is just copying it down. 0 ORed with 0 keeps the 0, 1 ORed with 0 keeps a 1. So we get the same bits except for bit 2, which we forced to be a 1. If we take the other example of turning that bit off, here I'll have here's bit 0, bit 1, bit 2 is on. We want to turn it off without affecting the rest. It's this command that does that, bit 2, and all of this stuff means turn that bit off with leaving the rest alone. But we start with a 1, we shift it 2 places, we invert it with the NOT logical operator, and then we AND this with the original variable, the original register. So we take this as our original, and this is what we've gotten with the not 1 left shifted 2 places. And we go bit by bit. So 0 and 1 have to be 1 to get a 1. So that stays as 0. 1 and 1, we keep a 1. 1 and 0, we get a 0. So here we flipped that bit. 1 and 1, it stays a 1. 0 and 1, it stays at 0. 1 ANDed with 1 gives us a 1, so it stays. 0 ANDed with 1 gives us the 0, and 1 ANDed with 1 gives us the 1. So we get the answer. So that's how these bitwise operators work. As you see, the Arduino people knew this was complicated, so they have things like functions to set the individual bits without having to deal with anything else. But down deep, this is what is in the Arduino libraries, and you'll see them in other libraries sometimes too. So that's enough for now, I think. So we've looked at math in C, and again, I'm hoping you will start with good example codes and change them. Always use the print statement if you're not sure about things like math precedent rules and parentheses and typecasting and things like that. If you're never sure, print it out. Write a test code, print it out. That's the best way to verify how it's working. All right, I'll see you on the next video.